Hey, what's up, Chem Peeps? Mr. Boylan here, and what in the heck are we gonna do in this video? This time, we need to explain the role of indicators in acid-base chemistry. What are they for? Why do we need them? As always, breaking it down, this time into 3. 1. First thing we're gonna do, define an acid-base indicator. What the heck is it? 2. We're gonna explain how an acid-base indicator works. 3. We're going to explain the role of an acid-base indicator in an acid-base titration. So what is it? How does it do what it does? Why is it important in titrations? It's going to be a great vid. I can already feel it. I've got an indication. Okay, so first of all, we need to define what the heck an indicator is. It is just a dye that changes colors depending on the pH of a solution. And indicators are just examples of weak acids. So as we try to define what an indicator is, it's important to remember what a weak acid is. And there's the equation to describe a weak acid reaction with water. What we're going to do in this video is, because it's a weak acid, but our focus is on indicators, is we're just going to sub out that A for IND, short for indicator. But notice, it does the same thing. It acts just like a weak acid. And we'll set up the same type of equilibrium. Our anion is just going to be represented with that IND minus. Now, the protonated or acid form of our indicator is one color, and the deprotonated or base form of the indicator is a different one. I think the best way to understand what an indicator is to think of 2 really common examples, one of which is litmus paper. Litmus paper in the acid form is red, and in its base form, it's blue. Now, as you take a look at your screen, hopefully it makes sense as to why we're using IND to abbreviate that fairly complex anion portion, the indicator molecule in litmus paper. Notice that the protonated or acid form, got those hydrogens on there, is red. The deprotonated or conjugate base form, without the hydrogen ions, is blue. Another really common example is phenolphthalein. The protonated or acid form is colorless, and the conjugate base form is that beautiful pink, magenta, fuchsia color that we all know and love. Again, notice why it's so important that we abbreviate with IND. I mean, who the heck wants to write out these really complex formulas to describe the actual molecules of the indicator? So HIND is the protonated or acid form of phenolphthalein. IND minus, the deprotonated or base form. So the first part of this video, you have to define what an indicator is. It's just a weak acid, but it's special because the 2 different forms, the weak acid and conjugate base form, are 2 different colors. That's what an indicator is. All right, next thing we need to do is we need to explain how indicators work. And to do that, I'm going to use phenolphthalein as an example indicator. All right, so let me give you a visual here. In this dropper, we've got phenolphthalein. I'm going to put in 2 drops of my phenolphthalein indicator. In pure water, the colorless or acid form of the indicator dominates, which makes sense considering the Ka of phenolphthalein. So just dropping your phenolphthalein in water, it's going to remain colorless. I think the best way to explain how indicators like phenolphthalein work is to think about it in terms of Le Chatelier's principle. If you put this indicator in a base, hydroxide ions are going to react with and remove the hydronium from this equilibrium. Therefore, the equilibrium will shift, according to Le Chatelier's principle, to the product side to reestablish that equilibrium. And the product side is the conjugate base side, or the side in which the pink form will dominate. Let's think about what happens when we add a couple of drops to a basic solution. Loop, loop. Think about your equilibrium. There's a lot of hydroxide. It's going to remove a bunch of the hydronium and shift the reaction to the right. Boom! So in a basic solution, phenolphthalein is mostly going to be in its conjugate base or pink form. And that's why in heavily basic solutions, you'll see that nice deep pink color. Magenta, fuchsia. Now let's think about it in an acidic solution. And let's think about Le Chatelier's principle. If you add this indicator to a solution that has a bunch of hydronium ion, the equilibrium is going to shift to the left, or the reactant side. For phenolphthalein, that's the colorless side. In acidic solutions, however, let me add a couple drops. Bloop, bloop. In an acidic solution, it remains colorless. Adding it to a solution with a bunch of hydronium is just going to force the reaction even further to the left, keeping it in its colorless form, which is why in acidic solutions, phenolphthalein is colorless. Now, let's think about when that ratio is equal to 1. In this situation, you'll have a mix of both the colors of the weak acid and the conjugate base form. In terms of phenolphthalein, you're going to have a mix of colorless and pink. In other words, you mix them together, you're going to get a light pink. Now, why is this so important? Well, let's talk about now the third thing we need to take away from this video. Let's talk about the role of these indicators in acid-base titrations. If you have equal concentrations of the weak acid and conjugate base form of your indicator, at that point, the hydronium ion concentration will equal the Ka of your indicator, or the pH of your solution at that point will equal the pKa of your indicator. Again, as you think about why, remember that we're working with a weak acid, that essentially our indicator is a weak acid. And if the concentration of the weak acid and conjugate base form are the same, they essentially drop out of the Ka expression. Therefore, at the point when those two concentrations are equal, the Ka is equal to the hydronium ion concentration, and if you take the negative log of both sides, the pKa is equal to the pH. But let's think about a slightly basic solution. Bloop, bloop. There's enough hydroxide to use up some of this hydronium and shift this equilibrium slightly to the right. Boom! But notice it's only slightly pink. We still have considerable amounts of both the weak acid and conjugate base form in our solution. Which means you can use an indicator to determine the equivalence point of a titration if that color change occurs within the same range as the rapid change in pH for your titration. Therefore, big takeaway here, you want to choose an indicator for your titration that has a pKa that's closest to the pH at the equivalence point for your titration. So as you look at this example titration curve of a weak acid with a strong base, phenolphthalein makes a great indicator. And let's think about why. The pKa of phenolphthalein is about 9, which means that it's at about pH of 9 where the concentration of the weak acid form, or the colorless form, and the conjugate base form, or the pink form, are about the same concentration. So for a weak acid strong base titration, phenolphthalein makes a great indicator. It'll start to change color at about the equivalence point of the titration that you're working with. That's why you want just the faintest pink color when you're performing the titration. You don't want it colorless because at that point you have all of the acid form, and that's before the equivalence point. You don't want it dark pink because then it's all in its base form. All right, that's it for this video. Have a fantastic day.